Yes, Assalamu alaikum, dear students. We are uh, resuming the second half of the topic astronomy and cosmology, and this time we are starting with the emission spectrum for distant stars. Emission spectrum or spectra from distant stars. This is actually about what we observe when we observe the emission spectra from distant stars. This shows us a very important thing about how stars are moving. When we observe a spectrum in the lab, for example, this is a hydrogen spectrum with some lines appearing on a definite position. This is always the fixed pattern. That is why we call emission spectrum of any element is known as the signature of that element. So for hydrogen, for example, we have a fixed position of these lines that appear on this spectrum. One line that appears here is always 380 nanometer, then slightly away from it is a 500 nanometer line, then we have a 600 nanometer, then we have a 700 nanometer. So these are definite positions on a hydrogen spectrum. This is hydrogen spectrum observed in the lab. But once we observe the same spectrum using the light coming from a very distant star, this same 380 nanometer appears slightly shifted towards this side, which means the red. This is higher wavelengths. So we call it a red shift. This line appears here. And this is a very small shift that we observe. Let's say if this is 380 nanometer, this could be 382 nanometer. So 2 nanometer has shifted towards red, and this is called red shift. Now red shift means all these lines appear to have shifted towards red color, that is the longer wavelength of these lines. This red shift confirms what? That is interesting. That shows delta lambda, which is the change in wavelength divided by the lambda originally that we observe in the lab. This is nearly same ratio as V over C. V is the speed of that star with which it must be moving, and C is the speed of light. When we use these values in it, for example, delta lambda is only let's say 2 nanometer, because this line is suppose 382 nanometer. So when we take the difference, this is 2 nanometer divided by 380 nanometer. This is nearly equal to this ratio, with this equal to speed of light. If I use this calculation, the speed of the star comes out to be nearly 6.8 into 10 raised power 5 meter per second. This is the speed with which the star is moving away from us, and this is confirmed by the red shift. This is a very strong evidence in support of Big Bang theory, which claims that the universe is expanding and all things are moving away from us. But of course, there are questions that have not been answered so far, because in some cases blue shift has also been observed. Moving on, we can talk about what the implication of this is. Another important observation made was and that again in support of the Big Bang theory, that was Hubble's constant. So this Hubble's law, what does this Hubble's law tell us? This again confirms that yes, things are moving away from us. Most of the stars, most of the galaxies that we have observed, they are moving away from us at a very large speed. And when Edwin Hubble observed very large number of objects. uh, he had this observation. For very large number of stars and galaxies he observed, he plotted them on this graph like this. So speed with which they are moving away from us and the distance they have from the earth, they appear to have a relationship on this graph, and using a line he worked out a relationship between this, which is known as Hubble's law, that speed is directly proportional to distance of galaxies or stars. So this is equal to Hubble's constant times distance. So let's say it is the same speed we have just calculated. That speed was 6.8 into 10 raised to power 5, and I want to know what is the distance of that star from us. So using the value of the Hubble constant is nearly equal to 2.3 into 10 raised to the power minus 18, and this is calculated in second minus 1, and you can easily predict its units from this equation. Once I use this equation with the same speed we have just calculated for a star, suppose that V is used in that equation, that is 6.8 into 10 raised to power 5 is equal to Hubble's constant, matlab 2.3 into 10 raised to power minus 18 into distance. So I want to know what is the distance of that star from us. D comes out to be approximately 3 into 10 raised to power 14 billion kilometers. So this is the kind of distances we have commonly observed in the universe. Whenever we deal with their speeds, with their distances, we have such huge numbers. So that is one indication of the expansion of the universe, and it continues to expand. This is for one particular speed, but if we have slightly greater speed, still greater distances are observed. But even more important significance of Hubble's law is that using the value of this constant, Hubble's constant, we have estimated the age of the universe. For example, if this is the Hubble's constant, which is s minus 1, if I take the reciprocal of it, 1 over h naught, this is 1 over 2.3 into 10 raised to power minus 18, and this of course is in seconds now. What is the significance of this calculation? This time comes out to be 4.3 into 10 raised to power 17 seconds, which is 13.8 billion years, and this is experimentally confirmed age of the universe from another experiment which is very famous and for which several American scientists were awarded Nobel Prize. They confirmed the age of this universe, and Hubble constant theoretically gives more or less the same value that they experimentally confirmed. So this is a very significant constant, and it is used to estimate the age of the universe. So with this, we have covered the topic astronomy and cosmology. Of course, as I said in the beginning of my earlier lecture, that this is a very big topic, and you need to go deeper and look at the various related aspects if you really want to understand the bigger picture. But as far as the tiny bits are concerned, the small concepts which are covered in your syllabus, we have mostly talked about them. Thank you very much.